Hi, welcome to the NMR workshop. Welcome to the question 3. Okay, question 3 is about the cyclopropane. And we did a reaction, we get this cyclopropane, but we don't know which is the diastereomer that we have. Okay, we have the NMR that are part A, that is the most shielded. Okay, we have 4 signals. And then we have 2 sets of NMR signals that are B and C that corresponds to one of the hydrogens of the cyclopropane. Okay? First of all, when we start this type of exercise, what we need to do is to analyze the different protons that we have in the compound. Here what we have is the 4 more shielded protons will be obviously the 3 protons from the aryl group, from the benzene, plus the proton of the aldehyde. We know that this proton has to be between 9 and 10, and this can be between 7 and 8. Probably a little bit more than 8 because we have 2 electrons with rubbing groups that are putting that are shielding more the protons of the aromatic ring. But basically, this will be the most shielded because it's an aldehyde hydrogen, and then will come this 3. Okay, for HD will couple with HF. That means that will be a doublet. All the other couplings are so far away, we will not consider. Okay, HA, at first sight, I will say that is a singlet because it doesn't have any proton at J3. But we can consider that maybe it's coupling with HB. That means there will be a doublet, but with a coupling constant very, very small. Okay, because it's J4, it's not J3. HB will be a doublet with HC, but if it's coupling HA with HB, also will be a normal doublet, and then another doublet, but with the J very small, because it's a J4. Okay? And finally, HC will couple only with HB, this will be a doublet. Okay, if we analyze the part A of the spectra, what we have here is that we have a doublet, that this will be HD, okay, because it's a doublet, it's the one that is more shielded, that means corresponds to the aldehyde, and the coupling constant, if you calculate, if you rest these 2 signals, the distance between these 2 signals is 4.5 Hz. Next one, we have a doublet, but with a very narrow J coupling. That means it corresponds to HA, what we decided to HA. That means has to be a singlet, but maybe it's coupling at J4 and will be a doublet, but with a very small coupling constant. That means that this will be HA. Also, it's the more shielded because we have the 2 electron with rubbing groups in ortho position. Then we have here a doublet of doublets that probably corresponds to HB with a normal coupling constant of 8.6 Hz and a very narrow coupling constant that is 2.4 Hz that corresponds to the same coupling constant of this. That has to be the coupling constant HA-HB. That means that this will be HB. And finally, we have a doublet that must be HC. Okay? This has been easy. Check that the coupling constant corresponds to the structure that we saw. HC-HB is the same coupling constant that HB-HC, 8.6, 8.5, more or less it's the same. Remember that it's very difficult that it has to be exact the same number. If are similar, are okay. The narrow coupling constant is 2.4 for HBHA and HAHB, and then we have the aldehyde. Okay, then we will analyze these two signals that are HE and HF. Why? Because are the two signals that correspond to B and C. Okay. Why corresponds to B and C? Well, basically because these will be less shielded because we have an aliphatic substituent here, and also the coupling tree will be very difficult because we'll couple with HF, HE, and also we'll couple with the CH2 directly attached here, and it's not, HG is not one of the NMRs that we highlighted in order to do the exercise. That means B and C will correspond to HF and HE. In order to know which is each one, basically what we will do is to check the coupling tree of each one. HF, okay, HF, sorry, will couple with HD, doublet, will couple with HE, doublet, and will couple with HE. That will be another doublet. That means that basically a chief will be a doublet of doublets of doublets. This is what we have to see. The other proton is HE. Okay, HE has to couple with HF, a doublet, okay, and has to couple with HG, another doublet. That means that has to be a doublet of doublets. And now we analyze the signal B and signal C. Clearly, signal B is a doublet of doublets. That means that this will correspond to HE. Okay, we have a doublet of doublets. While HF has to correspond to C because we don't have any other option. But if we analyze a little bit the signal, here is looks like a quadruplet, isn't it? Basically, we obtain a quadruplet when we couple one hydrogen with three other hydrogens that are equivalent. Okay, the typical example is the signal of a CH2-CH3. The CH2 is coupling with all the CH3 that are all equivalents, and we have a quadruplet, a very nice quadruplet or quartet. Yes? But here, obviously, we don't have any three hydrogens equivalents. But HF is a doublet of doublets of doublets. He's coupling with three different hydrogens. What happens if this coupling constant between these three doublets are quite similar? Okay? If the coupling constant of these three doublets are quite similar, what we will see if the coupling constant HD if the coupling constant of JFD is similar to JFE and is similar to JHG, okay, if these three coupling constants are very similar, what we will see is that the signals will overlap and we will form will look like a quadruplet or quartet. Okay, it looks like this. Okay, if the three J couplings are quite similar. And what we calculate is that the coupling constant is 4.7 if we consider this is a quadruplet. And we can see that JFT, the JFT basically is this coupling constant, is very similar to 4.7. That means that probably what we saw is that all these three coupling constants are very similar, and for this we saw like a quadruplet. If you see the quadruplet in the real NMR, you will see that it's not a nice quadruplet, it's quite broad. This indicates that there are not three hydrogens that are equivalent, that probably is that the coupling constants are quite similar, but the hydrogens are different. Okay, that means that until now everything looks okay. This will be HF and this will be HE. We assign all the signals, and now we have to discover which stereomer we have. How we can do it? Well, basically, a cyclopropane is a fixed, it's a rigid structure. That means that what we have okay, sorry, is, for example, we have this aldehyde. Okay, this is HF, this is HT, okay? And what we know is that in a cyclopropane, if, for example, if HF and HE are both in front of the slide, the coupling constant, the dihedral angle, is 0. Okay? If when R in cis will be 0 degrees when R in cis, because both are in the same phase of the cyclopropane, if the cyclopropane is over the slide. Okay, and you can see that the dihedral angle between these two hydrogens is exactly 0. However, when they are in crans, okay, the dihedral angle is 120. Don't confuse with 180, because it's a cyclopropane, the dihedral angle has to be 120. Okay? And this corresponds to when are in crans. If we analyze this, we know that when they are 0, the coupling constant has to be quite high. But when it's 120, the coupling constant has to be quite small. I will say that in this situation it will be 4, 6, and here will be major than 6. Okay? This is a very general, that means it has to be major than 7, but okay. Okay? When the J is 0, it has to be bigger than when the J is 120. Then, we know that HE, okay, is coupling with one hydrogen with a big constant and with a small constant with the other. That means that HE I remove the Cartwright diagram, we get all the information of the Cartwright diagram. We know that HE is coupling with a J crans and with a J cis. Okay, one coupling is crans and one coupling is cis. If we go to HF, that is this signal, we decided that the coupling constant is 4.7 Hz. That means all the coupling constants are quite similar, we decided before, in order to form like a quadruplet. Okay? And we know, at least this is not a real coupling constant, but we know one real coupling constant. This is the coupling constant between HF and HD. We know this coupling constant because we calculate it thanks to XD. That is 4.5 Hertz. That means if in order to have a quadruplet the coupling constant has to be very similar, what we got is that HF has 2 JCs. No, 2J is cranks, not Cs. Sorry. Because the coupling constant is 4.5, that is less than 6. That means HF, if we draw HF up, HE and HG must be down in order to have a Kranz coupling constant. And then, if we draw it like this, we saw that HE has a cis coupling constant with HG, that will be big, will be 10 Hertz, and a Kranz coupling constant with HF that has to be small and will be 5.4. That means the final diastereomer that we have must be with HF Kranz to HE and HG, and HE cis to HG and Kranz to HF. Okay? Obviously here I draw one enantiomer, but we have a mixture of enantiomers. That means by NMR we cannot know which is the enantiomer. We only can have the relative configuration of the final molecule. But the relative configuration has to be this. HF in Kranz with HE and HG, and HE in cis to HG and Kranz to HF. Okay? I know that it's quite complicated, but if you go step by step,